And go ahead.
All right, good afternoon. Welcome to the CERIAS Security Seminar Series. Today is my pleasure to introduce Sergey Panasyuk from Air Force Research Lab. Sergey is a computer scientist at the Air Force Research Laboratory's Information Directorate in Rome, New York. He joined AFRL in 2008 and is assigned to the computing architecture branch. And in his current position, he focuses on research and development of technologies related to the application of advanced computing to information assurance and trusted computing. And Sergey has more than 9 years of professional experience as embedded computer system developer. Sergey received his Bachelor of Science degree in Computer and Information Science with minor in mathematics from SUNY Institute of Technology at Utica, Rome in 2002. And he received his Master of Science degree in 2008 from the same institution. Sergey.
Thank you for coming, and thank you for inviting to give this talk. So today we'll talk about assured processing through obfuscation. It's some results of our project at Rome Lab. So objective for this project was to evaluate obfuscation techniques, the current and potentially emerging techniques, as the way to assure processing of trustworthy computing on non-trusted machines, for example. So examples of this could be like a software vendor produces a software and sells it. How can they guarantee that the software would not be cracked or hacked? Obfuscation is good enough for that or not. Another example is you try to run a program on the cloud. So you don't know who owns the cloud. You don't know what's going on there. It might be not the cloud, but actually just a single workstation that your friend has. He has ability to not only capture your file, but analyze what you execute. He can take the trace, etc. So he can steal your file and then later analyze. So how do you protect the secrets, keep the confidentiality and integrity of the data and the code? If we compare it to cryptography problem, cryptography is used to protect data. So you can see on top over here, here's my mouse pointer, Alice and Bob, they trust each other and they share a key between themselves. So they can pass the information between themselves, and Mallory would not be able to see what the data is. So there's two major components to this: is Alice and Bob trust each other and they share this key. When it comes to obfuscation, Alice cannot trust Bob, so that's given. But Alice needs to give Bob a program to run on his computer. So there is no way that Alice can encrypt the program, because it should be run on the CPU that Bob has, and Bob knows the language the CPU is using to interpret the program. So that brings the question what Alice can do in order to prevent Bob from analyzing the program. So Alice potentially can use obfuscation to make the program so hard to analyze that Bob and Mallory, potentially together, combined, would find it not worth doing breaking the code. So when it comes to measurement of effect of obfuscation, we found it somewhat difficult because we're dealing with Bob or Mallory, and they are humans. So there is a professional reverse engineers, there is students. So how do you evaluate who is better, who is worse, and what kind of tools they use? So when it comes to code confidentiality integrity, obfuscation is good, but then when it comes to availability, it might be bad. Because when we obfuscate our code and put in cloud, we expect that our performance degradation will not be big. We expect that the modern antivirus would not say that our code is bad. And we expect that like certain obfuscation techniques like self-modifying code would be allowed to run, but it might be not the case in the future with like no execute, bit enable, etc. Another interesting positive thing of obfuscation is its ability to create a diversified version of the same code. You can imagine that if you obfuscate the web server and each version of the web server will be obfuscated a different way, then attacking this web server will be very difficult. You can attack one, but not all of them. So it prevents a generic type of the attacks against the binary. And our obfuscation techniques needs to be generally applicable, so you can obfuscate just any program, not require the developer to redesign the program for this obfuscation techniques to be applicable. Our approach was, we assumed that we're going to have a person with an ultra-mobile PC that would go into some kind of high performance computer lab or something like that, connect his computer and start executing the code from it. So we designed the prototype of the hardware as a USB mass storage device. It was emulated using Linux USB gadget framework. And most of the time we spent on obfuscation. So we looked at the existing obfuscation algorithms, what their pluses and minuses are, why they failed, and we tried to evaluate them not based on what most of the people use is try to run them in like IDA Pro or OBJ dump without the user interaction. We think it's important to put the user in because you may change just slightly the beginning of the code and IDA would not disassemble it, but for reverser it would take 5 seconds to fix the whole problem. So we spent some time learning IDA tools and trying to manually reverse engineer our obfuscation. So that's the part of the testing. We look into homomorphic cryptosystems. That's a big research going on of outsourcing computation to cloud especially. So it's great in theory, but not in practice. So if you look at the picture, we would like to have, let's say, X, Y, and Z elements that we would encrypt on our trusted system and produce X prime, Y prime, and Z prime components. Then we would send it to cloud and ask the cloud to multiply them. When we're going to get result back, we're going to decrypt it, and this decrypted result would be actually the product of X, Y, and Z. The issue number one is this encryption-decryption takes a long time, so it's not very efficient. The problem number two is most of the known algorithms are only partially homomorphic. Like RSA, it's good for multiplying but cannot do addition. The performance of RSA compared to, for example, shift operand is huge. You can shift by 2, which is increasing to the power, and in the RSA you would perform loop multiplication, which is very, very slow. There is one fully homomorphic algorithm published by Greg Gentry in 2009, and I think right now his thesis is available for public review. And the statement was that his algorithm is not generic, not applicable to most of the applications. So you need to actually redesign the application to use crypto systems for your protection. And we found it difficult to use a crypto system, especially when it comes to merging data and code. Because you can imagine you have a for loop and there is a counter. Would you encrypt the counter or you pass that counter as unencrypted element? Will that provide some kind of side channel attacks that would allow the adversary to maybe not get the full details of your code, but get the kind of draft idea of what you are doing? So we stick with obfuscation as a short time solution. We're not trying to protect for a very, very long time. There is certain obfuscation techniques that actually use crypto systems. The Packers is a very popular example where they encrypt the binary, send it to the machine, and then they decrypt it. Those systems are very easily broken, especially if you use active introspection, for example. You can monitor every instruction being executed, filter it, deobfuscate, and you're going to get the original code. Another interesting crypto technique for obfuscation is instruction set randomization. And that can be viewed as obfuscation as well, where instruction set is actually encrypted and during the runtime is decrypted by sort of like a Java virtual machine type of the virtualization. So when we looked into obfuscation, we grouped it into two different categories. The first category is source code obfuscation. This group deals with high-level obfuscation. It's applicable to open source components. If you did any web page analysis, you will see the web pages that actually utilize JavaScript to encrypt and decrypt themselves so nobody can steal it. Uh, Python scripts or Bash scripts that you use to build or run the system should be delivered as open source, so they can be obfuscated to hide what you're actually doing. Java and C#, like .NET languages, they vary. They keep a lot of information in a bytecode. It's possible to reconstruct almost 100% of the original source code from the bytecode, minus comments and formatting. Actually, the variable names, the local function names are preserved, which gives the adversary the ability to analyze not only what's written, but what kind of logic did you put into variable names. And that gives a lot of information that we actually want to try to hide. When it comes to C and C++, high-level obfuscation may be not as effective as some people think. For example, if you compile C code, local functions named are automatically lost. Local variables are lost. There is a very complex way of reusing limited number of registers that's available in the system. So you need to know calling convention, like how the variables pass to the function, how the local variables stored, is that through the stack or through the registers, how the call actually happens. All that needs to be known. And for example, if we look at IDA Pro approach, they try to recognize the compiler that we use to compile the code in order to disassemble how the calling convention is used. So it's very difficult to reconstruct the C or C++ code, and the best so far we know that IDA Pro plugin Hexray allows you to reconstruct C abstraction of the assembly, which is not necessarily compilable, but gives you ability to read it like a C code. When it comes to assembly, it's almost straightforward process of getting machine code to assembly. There is very little optimization done by the linker. It might be some pipelining optimization, etc. But usually there is no obfuscation done at assembly level. So you may want to obfuscate assembly code to prevent straightforward reversing. And high-level obfuscation, we made a conclusion, is very applicable to obfuscating, for example, protocols, how the software components communicate between each other. Not necessarily the program to program, but even class to class, what kind of APIs they use and how they call each other. Like obfuscating state machines inside of the program, and it basically used to prevent high-level analysis, like reconstruction of control flows, reconstruction of the diagrams that allow you to look at the picture and see how the program interacts within and inside. Examples are for Java, renaming variables, function, and classes is very, very popular. It's possible to actually move functions from classes to standalone functions in Java and rename, for example, read file API call to A12, and then it would be not obvious what's going on. The same thing is applicable to C and C++ if it's compiled to export functions. So if you designed a program and you designed the library that the program is using, you may wish to rename, for example, load file into, I don't know, read registry. And it would be very confusing for somebody who doesn't know what's actually going on. And with Windows DLLs, it's very popular to actually remove the names completely and use just a numbering scheme. So I'm calling API exported number 5, and you don't even know what it is. Extra variables and useless computation is very popular. Java doesn't do much of optimization in that regard, but when it comes to, for example, compiling the code with GCC, it may actually remove your redundant computation and leave only the results. So you need to make sure that you opt out the optimization of the code sections if you do it at the source code level. On the bottom you see the picture that's from Wikipedia that shows a very simple C program that prints out the prime numbers less than 100. it might be difficult right now to see that code, but if you would compile it and actually reverse engineer, it would be obvious what's going on. So that's the good example where obfuscation of source code level at C and C++ is not really useful. The second group is the binary obfuscation, or the low-level obfuscation. This obfuscation is applicable to the most applications because they distributed in a pre-built form. So like the whole Windows distribution is pre-built by Microsoft. In order for Bob, the bad Bob, to analyze what Alice provided him, he needs to reverse engineer it. And this is a very simplified reverse engineering process. The Bob would perform disassembly. Disassembly can be done by linear sweep or recursive traversal. Another very popular way is to do dynamic tracing. So Bob would run Alice program on his machine and monitor what CPU instructions were issued and actually work just on this set. The problem with that is Bob would get only subset of the Alice's program. Like if you think about serial number check, it's not necessarily that Alice would put it in the one single component. She might have a function that would be called, let's say, every other Monday. And the Bob would not be able to get it unless he statically disassembles the whole program, not dynamically. The next step would be control flow construction, where you construct how code follows from one instruction to another, for example. Then it's possible to do deobfuscation, like instruction reduction and simplification of the logic. And that step can be merged with step number 4, which is decompilation. That's what the hex ray from IDA Pro is actually doing. So when we look at the source code obfuscation, it deals with step 2, 3, and 4. That kind of prevents that of occurring. The binary obfuscation deals with step number 1 and step number 4. Because in step number 1, it's very important to prevent the disassembly. That's one of the critical steps. And step number 4 relies on how the assembly instructions are actually put by the compiler. And it's possible to insert just simple knobs in the code and prevent, for example, recognition of Microsoft for loop template for compilation. So all of the above steps, they depend on a proper disassembly. And proper disassembly is a very difficult problem because of the mix of data and code. When you compile the program, compiler may optimize how you jump. And in order to do that, it may mix jump tables, which is the data, with the code. Some of the static variables, like strings, may be mapped into not the data section, but the code section. And when you disassemble, you need to make a decision. Is it the code or is it data? And that decision makes a huge difference on how the results would look. And it's hard to compute control transfer, especially indirect transfers. So for example, Alice may write a code that computes a jump target and pushes that into EAX, and then she jumps into EAX register. How would you use, what kind of techniques can you use to actually see what the computation would be resulted in during the runtime, which is a very difficult problem. ABQ predicates is another very interesting area of research. That is, the if statement always resulted in true or false, or it may be intermediate. So that's the question that it tries to answer. And common assumptions, basically like the calling conventions. That's very important. If we can break that, then somebody needs to go and, for example, change IDA Pro to know what the calling conventions were used. Otherwise, it will not be able to disassemble properly. So, as just an example, created two different views of disassembly. One is a linear sweep. Remember, the third disassembly was the dynamic tracing. There is no smarts of getting the instructions themselves. You just need to monitor the CPU, and that can be done from within the virtual machine or emulator, for example. With linear sweep, disassembler would follow instruction after instruction. So it just follows byte after byte, and it doesn't take into account the jumps. So in the obfuscated program on the screen, you can see that we have 3 jumps. This is a jump number 1, which is unconditional jump. It's just going to jump one byte over, it's going to jump over byte hex 81. The second jump is conditional jump not equal. It would follow the compare statement. So if EAX and ECX registers are equal, it will execute this potentially byte 81. If they are not equal, it will jump to the third jump, which jumps to address stored in EAX register. It's just abstract code, not really runnable code, but something to illustrate what's going on. So when Alice compiles this program, it's going to result in this string of bytes on the bottom. The Bob would take the program, and first he would read a header, and the header would say that this program should start at byte 31 hex. And that's called the starting point, or program entry. The header describes a lot more information, but this is one of the most interesting for us right now. And that's where the disassembler would start actually analyzing the bit stream. So it would read the 2 bytes and interpret as an XOR instruction. The interpretation is very straightforward. All you need to do is follow the Intel or whatever architecture you're using instruction format and interpret the bits properly. So in this case, it interprets it as XOR instruction. Then we have a jump instruction, which is interpreted properly too. But then it would read 6 bytes and interpret them as a subtract. The reason is the OBJ dump, which is linear sweep disassembly, does not follow jump targets. So it doesn't know that we just jumped over this byte 81. And by doing so, we can actually hide this call to secret A within the subtract argument, the instruction. So the next instruction that linear sweep would show us is the compare instruction, and we potentially hide it secret A call from the Bob. The compare would be done properly, jump not equal would be done properly, but then again it interprets the next instruction as a subtract. Now this one is a very interesting one because if the OpQ predicate was used as a jump not equal, then the result was incorrect, potentially. But if jump not equal potentially can result in runnable code, then the result is correct. So the question is, how do you determine the difference between is this byte should be there or not? So it's a very difficult problem. And the idea of our code was if it continues, it will interpret this jump EAX. Well, I mentioned that EAX pointed to the call secret B. So we did actually run into the secret function B call instruction. This allows us to actually run 2 instructions. It allows us to run subtract and allows us to jump inside of the subtract instruction and perform the function call. And then the last byte would be interpreted properly. So just as a conclusion, we potentially can hide secret A, and we definitely can hide secret B. When it comes to recursive traversal, that's what IDA Pro is using, and the most advanced disassemblers, is they take into account that the jumps are very important information that we can use. So after interpreting the jump, the next instruction that IDA Pro would disassemble is what the jump is pointed to. It would actually jump over the byte hex 81 and reveal the call to the secret A instruction. Then it would follow exactly the same path, but it will fail on the next instruction because jump not equal is 2 branches transition. So it can fall into the next instruction or it can take the jump. And IDA Pro has no way of knowing in advance what's going to happen, and that's why they call it interactive disassembler. That's where the human should be involved, and that's where we actually can get the winning time by confusing the Bob, because Bob would need to sit here and analyze what's going on. So the weak point here is the human, not the computer. So a lot of obfuscation results that we see right now published, they target the tools, not the actual Bob. And then it will interpret the next instruction properly. But the interesting point is it would not see the last return instruction because there was no indication that this is the instruction. It interprets as just a data. So the question is, if this jump to EAX actually jumps to what the IDA thinks is unreachable code, can we hide something there? And the answer is yes. So some of the proposed solutions was to combine linear sweep and recursive traversal together, where the areas that not disassembled by recursive traversal disassembler would interpret it as a linear sweep, but then we kind of fall into the same problem of what actually happened. Is it correct or not? So as a result, we determined that overlapping instructions is a very promising area of research. They're very hard to find. But it's not only hard to find, it's, as we will see later, it's hard to produce. And that's why it's not very popular. It's very hard to analyze. As example, you can see the real snapshot that actually runs on the picture on the top right, where we obfuscated pop, EBP, and return, which is a very common end of the function in assembly language produced by GCC, and the obfuscated call. The obfuscated version basically, instead of searching for arithmetic instructions within the code, we just put them in. But it will be kind of the similar process to find existing instructions and put the code in. We would perform add, addition, subtraction, and then we'll call the next line, perform a subtraction, and then we'll call the address on the stack. That would result in the instructions that commented by semicolon on the screen. I don't have a pointer here, but with a mouse pointer I can show. So those instructions that commented with a semicolon, they will be actually executed after the call to ASP. The important thing that I wanted to illustrate here is it's easy to overlap one instruction, but how do you overlap the blocks? Because you need to transfer from one instruction to another that you want to execute after the first one, and just by overlapping maybe not possible because the instructions, the start of next instruction that you use for overlapping, like those hex 81 and ED, may be undesirable bytes that you have in the code. So you need to jump over them. So in order to do that, you need to insert with your overlapped code, you need to insert the jumps. And if you're lucky, you can use 2-byte jump instructions, but then you can jump only 128 or 256 bytes either directions, right? So it's very limited what you can do in overlapped area. We were successfully in hiding control flow, like a function calls, function returns as demonstrated in the picture. We hide jumps, including conditional jumps. We just overlap them with arithmetics. So if you try to disassemble the program in IDA Pro, you will see a whole bunch of subtract instructions ended with some kind of return statement, for example. And now you need to make a determination, is this return statement actually jumping somewhere in the middle of the instruction, or it just returns from the function? Hiding overlap instructions with APQ predicates is a quite interesting approach. There is mathematical functions like x squared greater or equal to 0. It's always true. So you can use those if statements to result in always true or false conditions. Another very interesting approach is to know API calls. So for example, you can read from dev0 and use that as the initializer to your variable, and then later on use that variable for something. So the disassembler, for example, can interpret or emulate some of the instructions and come up with a result saying that the mathematical expression would result always in true or false. But trying to put into disassembler all known API calls and library calls, that's something that probably would never happen. And you can use something very weird, like get register value XYZ, and you know that the register value always 1, for example. Another interesting result is when it comes to overlapping instructions, it's possible to overlap data as well. And it's actually, I read one of the papers where they showed example of how Microsoft used that. They overlapped the memory that's used by two different variables, and those two different variables were reusing 3 bytes of shared area, and one variable was used to determine if the system under debugger, another variable was used to compute some kind of algorithm that always resulted in 1 if it's not under debugger. But if it's under debugger, it will result in false statement. And if you just look at the arithmetical expression, you would not notice there was any differences because you don't know that the variables actually overlap. So when we were looking into overlap instructions, we determined that it's important for us to analyze how much area we have to feed the instructions. So we took 16 most eye-appealing application and DLLs from system32 folder of Windows XP Server Spec 3, and we wrote IDA Pro script that basically created statistics. We connected with Microsoft debugging symbols, and we kind of assumed that our disassembly is very, very close to proper because debug symbols were used. And as you can see, the move instruction, push, and call is the most popular instructions. So they take more than 50% of more than of the area, and then the rest of the instructions are rarely used. And when it comes to byte count per instruction, the average we computed was 3.1 or 3.2. So if you remove the opcode, which is 1, let's say, then you left with 2 bytes on average to put overlap instructions. So that's something very, very difficult. So when it comes to obfuscation by instruction overlapping, we're not looking to obfuscation of the whole program. We're trying to hide just very important transfer to that secret function that, let's say, checks the serial number or performs some kind of important algorithm. The constants and the offsets in the program represents what the static encoded integers are present, and they usually in small positive and small negative ranges. And that represents basically the local variables and the arguments that are being passed to the function calls. Another area that we looked into is we decided that concentrating just on low-level obfuscation would not be sufficient, so we looked into high-level obfuscation, something that would be done on the source code level. And this is a particular example where we took the program A on the left, down, left bottom, program A, written in C, and the program B, bottom right, written in C, and we marked the code lines with just A, B, C, D, E, F, constructed the control flow, and then we interleaved the control flow in such a manner that it doesn't matter which path it would be taken, both of the programs would run simultaneously. And that resulted in the control flow above. So the idea is that it would be very difficult for Bob to separate what the function A is doing and what the function B is doing. And if those functions are hard to separate, then he would not be able to modify the results of one without touching another. One way of attacking this approach is use a very smart slicing mechanism. If you can determine what the result variables relation to input variables, then you can slice the program separately and break it down. We rely on very heavy optimization by GCC, where it actually reuses some of the variables, especially when it comes to limited registers. So as an obfuscator, we implemented as a pre-assembly processor. We took original GCC that installed in the system and replaced it with our script that runs original GCC with -s flag passed to it. That results in assembly output of the compiled C program. Then we run our obfuscator that performs hiding of, let's say, jumps, etc. And in the future, we envision that to be something that the Alice would control, because Alice need to provide the input what the important areas of the program to obfuscate. It's very flexible and easy to customize because it's a very simple text processing program. It was very interesting to discover that you can do in assembly language the things that most of the people do in binary writing, just working with the binaries. You can insert bytes and modify the instructions just the way you want it. You can, for example, force jump instructions to be 4 bytes long instead of compiler optimized 2-byte long jump instructions. With overlap instructions, we're able to hide and protect from modification the instructions. I ran into the problem of debugging. I was debugging my code because I had a failure, and I was stepping through overlap instruction. And while you step, what the debugger does, it replaces the opcode of the instruction with C3, which is the breakpoint. And by replacing the overlap instruction with C3, it modified another another overlap view of this same memory, and it resulted either in crash or the failure. So modifying one one view kind of crashes another, which was a positive kind of anti-debugging technique that might be used. And we were successful in overlapping the small blocks, the blocks that consisted of instructions not longer than 5 bytes. So, and it's very limited because the more instruction we overlap, the more artificial code we need to insert, and that brings the possibility of detection of what's going on. We investigated multi-application area. There was interesting research where the parent-child as a debugger and debuggee is used. By default, Linux allows only one application to be debugged by debugger. Well, only one debugger to be attached to application. So if we attach ourselves to the application, there is nobody else can attach. There is a possibility of using the hardware debuggers, but they more difficult, or it's possible to use virtualization techniques, which is common. So this is something we tested, but didn't go that path too much. Virtual machine and instruction set randomization is very easy to implement as a debugger and debugging scenario. And we need a new toolchain. It would be something very good to have a GCC compiled with overlap in mind, something that would possibly compile specified code using very small instruction length, so it will be easier to overlap it. Detection of obfuscation is very important for us. We decided that if, for example, if you use a packer, it's quite obvious there is something wrong with the program. I think in the future it's possible that packed application will be not allowed to run because most of the malware that we see right now is packed. So if we just ban packed applications from running, that's the possible way of preventing some of the attacks. Overlap instructions are hard to detect statically, but it's easy dynamically, because when you run it, you will see that there is something else executed from different offset. And the question is how much effort it would take to actually create a shadow view for the Bob so he can see that 2 blocks is overlapping. Another technique was proposed by one of the students that worked over summer with us, was to perform excessive disassembly. Basically, disassemble the program from every possible offset, throw away all incorrect instructions, and if correct disassembled instructions are connected between themselves with like a jump or some kind of transition, then potentially this is the inserted overlap block, which was kind of interesting idea, but it takes too long to run. I think his code ran a couple of days and didn't finish. So, it's very excessive amount of processing to do. Merge control flows, and this is something that we did at the source code level. They don't look unusual in disassembler, especially if we overlap very small functions. The problem with control flow merging is if, let's say, if we go back to this example, if the function A would call function C inside, then it would complicate merging in such a way that it would become kind of jumping over and over and over. Potentially, you would need then to overlap B with C, and becomes kind of a massive problem. So we didn't solve that yet. So we work on at single function levels. Ability to remove overlap instructions can be removed, and it's possible. We see it as the cloning problem, where you basically take the overlap instruction and clone it somewhere else and modify the jump targets. But currently there is no static disassemblers that we know about that can actually perform it. And tracing is basically, I already mentioned, it's possible to do so. We think it's interesting to note that if there is modification to the disassembler that needs to be done, then obfuscation is one-time solution, because it will take, for example, 2-3 weeks for somebody to create a script for IDA Pro that will fix the problem. So how can we find the obfuscation technique such a way that it would be undeterministic, so it will not be possible to create a unique script for every obfuscated program? Merge control flow separation is possible. Basically, if you know input and output parameters, you can perform slicing. Performance, we took BZIP2 utility, can basically hide all control transfers, and it resulted in 25% slowdown. So now you need to decide for yourself, is obfuscation worth doing or not? Because if you run something on your smartphone, for example, and it takes 2 hours, and then you push it in the cloud and it runs 3 hours, it was definitely not worth doing it. And the new obfuscation techniques that are being developed right now that use heavily rely on virtualization, they perform 1% of actual work and 99% of the noise. So you can anticipate what kind of slowdown there. But those types of obfuscation is used for the malware, and they not in a rush of doing something. They can actually see it and sleep for hours. And actually it's good for them because they can avoid antivirus. But when it comes to the good wire, that obfuscation techniques might be not applicable. The size, it was not a dramatic increase in the size, so we were kind of happy with it. So as a summary, obfuscation is reversible, so it's impossible to protect your code by using the currently developed obfuscation techniques for a very long period of time. But you can succeed for 3 to 4 days, and maybe that's what you need right now. So there are some applications that should run only 3-4 days with the secrecy in mind, and then after that it doesn't matter. You already communicated to your servers, and those servers offline, and you're safe to go. And it's really relies on secrecy of algorithm. And once the obfuscation technique is published, it usually takes the next conference to publish how they obfuscated the code. So it's really fast. And the obfuscation time is inversely proportional of cost of secret. If you look into the commercially available applications and how long it took to crack or hack them, you'll notice that it's proportional to the cost and the demand for this application. So if the application is really important for people, it will be cracked really, really fast. Obfuscation level, source code with binary, it's very difficult to say that only low level or high level should be used. Both of them should be used, and actually it's possible to create a good obfuscation if we combine obfuscation techniques in such unpredictable order that the Bob would not know what to do first in order to result in the successful step later. Like, for example, he would need to remove overlap instructions first and then do control flow and flattering, or should he do control flow and flattering first and then perform something else? So maybe those mixes would be more successful than just relying on a particular single point. And again, it's very important to determine the difference between crackers and hackers. The cracking of application basically relies on trying to find a single point in the program that should be changed in order to succeed, in order to achieve your goal, while the reverse engineering of the whole program requires analysis of what's going on in the program, how the components interact between themselves, basically trying to extract the algorithms. So if you try to write a key number generator, it's a lot harder than just crack that the program is activated, for example. Obfuscation tools like Packers, it's very, very popular. but and they're popular not only for malware, they're popular for small companies that develop the software. Um, but it's very easy to detect that the program is obfuscated, and once you detect that the program is obfuscated, you know there is something interesting inside. So you kind of attract the bad guys trying to analyze what's going on. Avoidance of detection is very important. If you can avoid detection of that secret call, then it doesn't matter. So basically, then it goes to dynamic analysis, how you avoid dynamic detection that you actually called something. Um, and diversity of methods I already mentioned. It's basically trying to mix the methods in an unpredictable way. What next in obfuscation? Emulation and virtualization is becoming very popular right now. And it would be interesting to see something with architectural support. Like, can we tie a TPM type of the device to obfuscation? Can we ensure, like, if I give my code to Bob, can I use his TPM encryption key to encrypt my code such a way that only CPU with with TPM can decrypt and run it, but Bob himself will not be able to do that. That would be very interesting. Maybe not a TPM device, but something. Intel attempted to do that with, I think they called HDCP, which is HDMI protection protocol that they implemented. HDMI monitor receives encrypted signal from a video card. The video card doesn't see decrypted video, so all the communication is encrypted. But they didn't follow proper cryptography, and I think September 7th or something like that, the Intel HDCP master key was published. So pretty much they broke the whole thing, and now you can actually build your own Blu-ray players by using that key without paying any fee to Intel or doing anything with that. And this is the list of what I think is the most important references. I think we have at least 4 times that amount of papers analyzed. Some of those papers talk about overlap instructions, how they're used. It's not something new. I think the first reference to overlap instructions was done in 1992, where they were suggested for obfuscation, but then they were dropped because nobody wanted to use them. And overlap instructions were used in embedded systems to minimize the code size. So sometimes if you look into obfuscation, the techniques that being used in normal software development process is being kind of transferred into obfuscation. So maybe it's something that you know that might be not obvious as obfuscation techniques can be used as obfuscation techniques. So that's something that we're looking into. Is the input from you is like what the obfuscation is it can be done. Well, it's kind of been proved that it cannot be done, but maybe it can be prolonged, and etc. Any questions, interest, advices, comments? Yes.
Yes, seeing as the current tools are being used to generate one output, can we, when we try to apply obfuscation, can we have transform one program to the like two output like programs? See, two programs that can work together to achieve the similar functionality, but it will be very difficult to.
Yes, that was a part of two-in-one approach. Right now it shows only 2 functions being merged, but we merged gzip and bzip2 together by overlapping the function calls. So it's very complicated once you start running the function read file from bzip2 and it ends earlier than read file from gzip2 and keep the sync between the 2 programs.
What I suggested essentially, instead of merging, can we split? So they can, at the runtime, they will work together somehow.
Oh yes, that's basically what I tried to talk here was, I think I lost it, is the debugger and debugging. Yeah, that's type of solution. Some people use that within the single program. They use exceptions, like exception handlers. So they would run into the illegal instruction like divide by 0. Exception handler would be called. They would perform whatever instruction should be called, put the register values, and continue on. So like exception handler, it basically dividing the program within, but keeping the code at the one binary, and then yeah, inter-process communication is another very good example. And the current obfuscation techniques like Microsoft activation is a very good example, where you have a trusted site and you have untrusted site, the customer. And untrusted site performs computation based on a trusted input. And this way you can guarantee that you're not going to be hacked. But then you can apply another techniques like replay communication, etc. Anything else?
So I have a question about the performance. So what is your observation of the performance of runtime performance of the obfuscated program in comparison with the original version using different levels of obfuscation technologies?
Well, we did only...
Is that of a main concern, like the performance of the obfuscated?
Yes, yes. I think that falls into kind of availability of CIA, because if you are a bad guy, you're not concerned with performance, because it takes you longer to get into the machine, etc. But if you're a good guy, you want the customer to be happy, right? So that's where the performance actually matters. And if you do computational outsourcing, like you pushed your program into the cloud and it takes 3 times longer to run than on your laptop, then it didn't matter, right? So we view performance as very important.
So do you have any like specific approach to improving performance of obfuscated programs?
Well, that's why we try to advise minimization of obfuscation. Don't obfuscate the whole thing. Obfuscate a very important part, and that's where we feel the overlap instructions come in place, because it's possible to hide something very tiny in your program that transfers the control flow, for example, right? And your program would run normally, but then this transfer would be hidden, and maybe that would be enough for you to hide some activity. If you use the packers were successful on performance, because once it's unpacked during the load time, the rest of the runtime is wherever the original application was, but then it's very easy to detect.
Any other questions? If not, let's thank our speaker.
Thank you.